A single bond consists of one pair of electrons being shared. It's the lowest in energy and it's the longest bond length. Double bonds have two pairs of electrons being shared, and triple bonds are the shortest, strongest, and you have three pairs of electrons being shared. A sigma bond is formed by the overlap of orbitals in the same plane as the atoms, while pi bonds are formed above and below the center plane. What you need to know is that a single bond is a sigma bond. So we're going to represent sigma with the red line and pi with the white line. So if we were drawing a single bond, it would just be a sigma. While a double bond is one sigma and one pi. And a triple bond is one sigma and two pi. So go ahead and pause the video and count up all the sigma and pi bonds in this picture. So each single bond is a sigma bond, and each of those double bonds consist of one sigma bond. So I'm going to highlight each of the sigma bonds so you can double check yourself. And you should have gotten 27. Then my pi bonds should be the other bond in the double bond. And so you should have gotten 6 pi bonds. Go ahead and pause the video and try this one on your own. To do this one, you need to draw out the structure, figure out how many single, double, and triple bonds you have. So to draw it out, I had 8 carbons, 3 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens, 1 hydrogen, no hydrogens, and 2 hydrogens. So now I can go back, and each carbon should have 4 bonds. I can't add one there because then that carbon would have 5, so I have to add it on the right. And so that's the structure. Counting up my sigma, I get 19. So it must be A. And if you double check, we have 3 pi. Resonance occurs when one or more valid Lewis structure can be written for a particular molecule. Go ahead and pause the video and draw the Lewis structure for nitrate on your own. Restart once you have the Lewis structure. Your Lewis structure should have looked like this. Notice though, I have my double bond on the right oxygen. I easily could have had it on the bottom oxygen, and it would have looked like this. Or I could have had it on the left oxygen and made it look like such. All of these are correct. And actually not one of them is correct, all three of them are correct. It's a hybrid of all three of these. So you have to draw all the Lewis structure and put those double-headed arrows showing that not one of them but all of them are correct. We know that not one structure is correct because the bond lengths of nitrate are all the same. We would expect to see two long bond lengths and one shorter one if only one of them was the correct structure. But because they all have the same bond lengths and the bond length is between a single and a double bond, we know that it must be a hybrid or a mixture of all three of these. And that double bond is actually spread between the three nitrogen-oxygen bonds. You do not have to draw all of the Lewis structures if it doesn't say show all resonance structures. But be careful on the wording of the question. Formal charge is the number of valence electrons on the free atom minus the number of valence electrons assigned to the atom in the molecule. To calculate the valence electrons assigned, it's the number of lone pairs on that element plus half the number of the shared electrons. So if we were to calculate the formal charge on sulfate, first we would need to draw a Lewis structure of sulfate. So here's my Lewis structure for sulfate. To calculate the formal charge, you calculate it for each element. So for sulfur, sulfur normally has 6 valence electrons. So that's the number of valence electrons on the free atom. So it's going to be 6 minus the number of valence electrons assigned. Sulfur doesn't have any lone pairs, but it has 4 bonds. So that's 1, 2, 3, 4 shared electrons then. So it has a formal charge of 2. While each oxygen also normally has 6, it has 6 valence electrons plus 1 from each bond. So that's 7. So oxygen has a formal charge of -1. The formal charges need to add up to the charge on the atom, and you want the more electronegative atom to have the negative charge. So let's look at this way of drawing sulfate and figure out what its formal charge is. Sulfur again is 6 minus, we have 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. On the single bonded oxygen, we have 6 minus 6 plus 1 is 7, giving us a -1. And the oxygen with the double bond, we have 6 minus 6, which is 0. So based on formal charge, the sulfate ion with the double bonds and single bonds would be preferred over the sulfate ion with only, because the formal charges are lower and the -1 formal charges are on the electronegative oxygen atoms. So remember, the rules for a formal charge is the sum of the formal charges of a molecular ion must equal the overall charge on that compound. And you want to choose formal charges closest to 0 and with the negative formal charges on the more electronegative atom. So on this one, I'm going to give you the 3 structures for xenon trioxide, and you decide which one is best based on the formal charges. So go ahead and pause the video and decide which of these 4 is best based on the formal charges. So on the first structure, xenon had a formal charge of 8 minus 5, giving us a 3. And each of the oxygens are the same, 6 minus 7, giving us a negative 1. We'll look at the next structure. Xenon is an 8 minus 6, giving us a formal charge of 2, and oxygen. There's 2 types of oxygens. If we look at the single bond, we have 6 minus 7, giving us a negative 1. And if we look at the double bond oxygen, we have 6 minus 6, giving us a 0. The third structure, you have 8 minus 8, giving you a 0. And all of the oxygens are the same, 6 minus 6, giving you a 0. And looking at the last one, xenon is 8 minus 7, giving you a 1. And this double bond oxygen is 6 minus 6, giving you a 0. And the single bond oxygen is a 6 minus 7, giving you a negative 1. So the third structure is the best one. This is how it will look on a test, where you're given the structures and asked which one would be better based on formal charges. Or you could be given just one structure and asked what the formal charge of a particular element in that compound is. Let's look at 2 more. So this is how it also could look. I'm going to pause the video and try this one on your own. Oxygen is 6 minus 6, giving you a 0. And the other oxygen is the same. On C, you have 6 minus 5, giving you a 1. And 6 minus 7, giving you a negative 1. So 1 was the better structure.